Hello everyone. In today's video we're going to be tackling the same problem that we posed in part A of this video series, where we essentially have a bar that is being heated up, and on the inside of the bar it's all 20 degrees Celsius, and then on the two sides you have 50 and 80 degrees. And essentially what we're doing is we're measuring the thermal diffusivity of the bar throughout and seeing how the heat propagates throughout this bar. And so we use the von Neumann stability approach to calculate our thermal diffusivity with a change in time and position. So the issue with that one was if we had a value greater than 0.5, the graph that we created would be completely unstable and just look like a mess. This time, however, we are going to use a new method that will help supplement that issue, that error, and we will be able to tackle a broader range of numbers with that, and that is known as the Nikolson method. So, to start, we need to utilize the same equation. Let me get this chair over. We need to utilize the same equation that we derived from the beginning of the video last time. So that'll look like the following. Tj, and actually I'll wait to say that. It's Tj n plus 1 is equal to Tj to the n power times, or excuse me, not times, plus our alpha delta t over delta x squared times our Tj plus 1 to the n power minus 2 Tjn plus our Tj minus 1 to the n power. Okay. This is what we started with last time. We're basically going to add on to this with the Nikolson method. So what we will be basing this new derivation off of is the following. Use a different color. This will be from the following partial differential equation. Okay, so using this partial, we can base this off this partial through our thermal diffusivity and the change in temperature as well as our position. Right. So to start off, let me rewrite. This is going to take up a lot of space. So we have the same function on the left side. And then we have our R value. And then we will be adding a 1/2 in here times our previous function here at time of n minus 2t Jn plus Tj minus 1 to the n power plus, and then this will be like the newer function. So we'll be also analyzing a function at time n plus 1, and we will continue our derivation that way. So this will be plus Tj plus 1 to the n plus 1 time minus 2 Tj plus 1. Oh no, I had it here. Sure. N plus 1 plus our Tj minus 1 n plus 1. Okay? So there's a lot here. I'm stepping back so you can see it all. This is our full equation here. And I've kind of like color-coded the newer, yeah, you can see that. I've kind of color-coded the new additions to this equation here. So not only will we be measuring this from time n, but also time n plus 1. And what we're going to do now is we're going to separate those two time pieces. So we'll have our time n plus 1 on the left, and our time n on the right. Additionally, our r value is being multiplied times the 1/2. So we can just put this all together and make that our new r value. Okay? So I will separate the two time variables on both sides of the equation and do a few simplifications for this equation. So start negative r times t n plus 1 j plus 1 minus 1 plus 2r times t j n plus 1 minus our r t j minus 1 n plus 1 equal to our time of n. So negative r. Try and get out of the way so you guys can see what I'm writing. So be negative r t j minus 1 to the n power plus 1 plus 2r times our tjn plus r times t j minus 1 to the n power. And what we do know, just from looking at this equation, is if we are to set our time n to 0, then these temperature profiles are suddenly known. However, for n plus 1, that wouldn't be the same. That wouldn't be the case. So we're going to essentially put our function into a matrix, and we will be able to acquire some temperature profiles. Alright, so now that we have developed our equation, as you can see here, might be a little hard to see with the lighting in here, but now that we have this, we are able to create our matrix for our temperature profiles. So to do that, we need to create a matrix, basically like an equation with a product. So to start, we are going to create essentially a 98 by 98 matrix. And what I'm going to show here is just a little like snippet of one of the portions of this matrix, specifically this would be the top right of the matrix, or excuse me, top left of the matrix. And we will also be multiplying these by another matrix that is a 1 by 98. Alright, and with this, we have our temperature profiles here of each discretization that is on the inside of the bar. So we have our left-hand side of the bar. This will be TL, and then we'll have our T1, our T2, T3, and then our T of our 98th discretization, and our TR. Okay? And with this, we can provide corresponding values based on this equation that we derived to put in our overall matrix. Okay. So to start, we're going to go with our T2, and essentially what we can do, I want to do this, yeah, okay. So if we take our T2 and we implement this into our equation, we have temperature, our J would be equal to 2, our J minus 1, if that's equal to 2, then we get 1, and then our J plus 1, if we substitute that in, we get plus 3. And with this, we can sub in the appropriate values that will go in. So here, for our, so this creates our T3, basically, right here. And this yields a negative R value. So I'll create a little plot here. You get the point. And so with this, okay. So with our T2 value, we plug that in. Normally, we get 1 plus 2R. We plug in for our J plus 1, we get our third temperature, and then that yields negative R. And then we also get negative R for our T1. Okay, so that's our second temperature. Now if we go into our first, we plug in 1 for each of these. We'll get 1 on that one, on J. With J minus 1, we get 0. And then J plus 1, we get 2. value will yield 1 plus 2r, and then our j plus 1 will yield negative r. And we don't know this, so this value would go beyond the matrix here, and this would just be a 0. But additionally, any value that doesn't get filled in within our matrix is just a 0. And you can slowly start to see that this creates a diagonal going all the way from the top left corner to the bottom right. Imagine this extends 98 more rows, or I guess 96 more rows. So, with that, we can just fill in the values. And once again, any value that isn't these three, going from one discretization in your left and right portions adjacent to it. Anything else is just a 0. So 0, 0, 0. I guess it's not even in a matrix, but you get the point. And so now we can multiply our 98 by 98 matrix by our 1 by 98 matrix with our temperature profiles to create a product of the two. Okay. And simply, all we have to do here is multiply each component from our matrix times our temperature profile. So our T1 is a very special case that we will get back to. So we know our T2 and T3 straight away if we just multiply T2 times each value that is written. So let me also do this thing here. Okay. And so we will yield the following equations if we just multiply across. So here we have, for 2 we have negative r times our first temperature, that's what it is, n plus 1 plus 1 plus 2r times T2 n plus 1 minus r times T3 n plus 1. Sweet. And then if we do the same with T3, we get more or less the same thing, negative r T2 n plus 1 plus 1 plus 2r T3 n plus 1 minus r T4 n plus 1. So I mentioned how T1 is a special case because there is no T0 temperature profile, right? Because that would just be our left side of the bar, right? But we already know the temperature of that. With this matrix, what we're doing is we're finding the 98 unknown temperature profiles. And so with since the next part of our, or the first part of our profile for our temperature 1 is RTL, we can kind of, in a way, use that in our equation, right? So if we look at this equation that we came up with, so if we utilize this top equation, we can create a new equation to help with obtaining our first temperature profile. So yeah, let's do that. So from here, we can get 1 plus 2r T1 to the n plus 1 minus r T2 to the n plus 1 is equal to r T2 to the n power plus 1 minus 2r times Ti n plus 2r TL. And with this, we're able to use this right-hand side for our product, our first temperature profile. And so, we're just writing that how it is. I'm gonna, I'm gonna rewrite this so it's a little clearer, more organized rather. So that'll be 2r TL. So we're going from our left-hand side of the bar plus 1 minus 2r T1n plus r times T to n. Okay. And now that we know this, our right-hand side of the bar is essentially the same thing. You're just flipping the 1 and 2 to the 97th and 98th discretization to acquire the following. So you have r times T 97 to the n plus 1 minus 2r times T 98 plus 2r times TR. Okay? So now we basically have our first and last discretizations here and here. And now if we want to make it so our time is no longer n plus 1, and we want it to be previous time of n, we can change our second and third temperature profiles to do that. So, if we do this, we just remove our n plus 1s. These just become n. first equation, or first profile, this becomes positive. Oh my goodness. And then, similarly, in our second and third, the signs flip to be like that. And because of that, these signs also flip. And these ones do as well. These are negative R's and positive again. Yeah. That looks good. So that's basically how you find these temperature profiles through a matrix. We are going to plot these up so it's a little more clear so you can visually see it. And let's do it. So now that we have created our matrix, we can now create the plot encoding for the Crank-Nikolson method. So this is our von Neumann coding here, and we'll be referencing a few things from here. So to start, you need to make sure you have SciPy downloaded as well, as we will be using the linear algebra solver from that. So to start, I will kind of rewrite a lot of this coding here. Okay. So like we'll be using the same n, which is the number of discretizations. We have t equal to np dot full n 20. Oops. We have our first part of the bar, the left-hand side. This will be in position 0. That is equal to 50 degrees Celsius. Our final discretization, our right-hand side, this will be at the final spot, and that is equal to 80 degrees Celsius. So, utilizing the equation that we derived from the beginning, specifically, we can, hold on, actually before I do that, we also need to include our R value, and we will set this equal to 2, or, I mean, anything greater than 0.5, something to make it, to ensure that it will be unstable. Okay. Just run that. Okay. And we will copy our, no, it's okay. So yeah, we're going to copy this equation that we derived way up top. So we have np dot full, and then n minus r. We got np, I'm sure this is the same thing. Yeah. Hold on. Okay. And so this will be 1 plus 2r, because now you are, like take our second temperature profile here, you have negative r, 1 plus 2r, and negative r again. That's exactly what we have here. And we're going to put this whole thing in an array, like so, and we will essentially smush those together in an NP stack. And we will label this AB. Okay, make sure this works. Oh, right. This has to be multiplied. Okay, I think this needs to be in parentheses as well. I don't think you can make... Yeah, because that can't be an array straight off the NP stack. So, now we'll create our B variable, which is essentially going to be our... So, okay, hold on, pause. So our AB, which I just coded up, is basically this equation here. This is our our first temperature profile. I completely misspoke. But our B is actually the equation that we derived. So we have our R times T, and then we have our array, and we're going in the second position because it's going to be j plus 1, right, plus our 1 minus 2r, 2 times r, times times our temperature profile that's in the center. So like, yeah, so basically our 1 plus 2r, how that comes here, or tj to the n plus 1. Yeah. Plus our third component, which is r times t, with an array of 2. Okay. And so, when we have this line of code here, this is going to exclude our yeah, so I would just miss a -2 here. Okay, so I just forgot to include this negative here. Anyway, if we want to let's see, we need to create an array from our first part of the bar. Okay, as well as our last part of the bar. So on +2, that's 1. Okay, that looks good. So now we can use our SciPy linear algebra solver, and the way we're going to set up this variable is actually with an array, because we want to essentially exclude the first discretization to the left-hand side of the bar. And that'll be our SciPy lin alg.solve. And we will also be using the banded function. Okay, let's make sure that works. Okay, so we also need to adjust our shape size for our end value, because this is going to have a shape size of 100, I believe. So we have to account for that and decrease our ends to being n minus 2. Let's try that again. Sweet. So now if we do t, it'll perfectly show you the temperature profiles for the 100. It actually looks like more than 100. Temperature profiles. So that looks good. We can clear this out. Now we can include our temperature profiles so we can add our temperature profiles similar to how we had in this von Neumann stability analysis. And we will just be copying using tcopy. Okay. Oh, that's not good. Okay, hold on. I'm going to just comment this one out as well. Alright, so now that we have all this, we can move this up here. Okay. And we can then put our bees in a for loop for I in range. We'll do 1,000, fairly similar to what we used on the von Neumann stability analysis. Okay. And we can move our SciPy code into the for loop as well, and then we can take our temperature profiles and append them. Let's see if this works. It does. To T profiles. Well, those look pretty good, actually. Those look very good. This is going to just keep going forever. Let me close that. Hide. Nope, wrong button. we can, and to plot this, we can just take our code from the von Neumann plot, and hopefully this works. Beautiful. So you can see there are some larger steps that this has to take. Yeah. But as you can see, what we managed to do this time, without any error, like from the von Neumann, was we were able to take an R value greater than 0.5. Let's just do 0.51, just for kicks. So you have significantly larger steps here in the place the von Neumann would start to become unstable. So now if we really jack up the R value, we'll do 10. You get basically linear lines just stacked on top of one another. Let's try 100. Ooh, look at that. Zoom in a bit. Let me do a few more data points. Sweet. Oh, that's so cool. So basically, what's happening is because here, let me show it here. Because we have our R value, which we found in this equation before I erased it and everything, our R value was R equal to our alpha delta t over 2, because we had that 1/2 delta x squared. And essentially what's happening is if you were to change this distance, this 2, the 1/2, to like 1 over, we'll say 1 over 10, that value would increase in magnitude significantly. That would go from being 10 to 1 over 100, you know. We can, and I just show that actually. There's a huge difference in between those two. And with this, the initial conditions can drastically change how the temperature profiles will be outputted when being discretized.